All right. Hey guys, so welcome back to another video. So today I'm going to be talking about the fundamental theorem of calculus, or as it's usually abbreviated, the FTC. So basically, everything that we've done up to this point so far in the quarter has been to prepare you guys for doing the FTC and applying the FTC, right? So this is kind of like our big thing in calculus. It's so I've been pushing for you guys to think of the definite integral as a kind of like an adding machine, right? Takes a bunch of things within the interval and just adds them together, right? So the reason being is Riemann sums don't give us a super accurate way if we just pick like a very small set number of rectangles that's like feasible to do by hand. But what the FTC does is it allows us to kind of take an infinite amount of rectangles, right, that are infinitely thin, so we can fit as many of them inside as possible. And that gives us a really accurate and efficient way to kind of compute the definite integral for curves that like maybe that are kind of like curvy and squiggly, right? So we can't have like real shapes for them. Right, so the FTC comes in two parts. The first part, which I have shown up on the blackboard right now, is kind of just a way that kind of connects the derivative and the definite integral together. So it kind of like elaborates more on that relationship, right? So it seems very lengthy and complicated, but the real meat of the FTC, the first part, is just this part right here, because what this part tells us is if I take the derivative on both sides, right? When I take the derivative on both sides of this equation, I'm gonna get this thing in the box, right? Because the derivative of capital F is going to be f prime, and then the key thing is if I take the derivative of the integral side, what I'm going to get is just the integrand. So what that tells us is it gives us the notion that the derivative undoes the integral, right? And so like now we have a very concrete proof, an example, and theorem about that, right? It also tells us some other stuff about how like capital F is continuous and differentiable, but we won't touch on that too much for right now. The second part of the FTC is also a little bit complicated looking, but it is a little bit shorter. But the real key part is this equation. Down here, right? Because what this equation tells us is it gives us a way to compute the definite integral in a very efficient and clean and accurate way, right? What it's saying right here is based on FTC part 1, where I have that capital F of x is the integral of little f of x, right? What that tells me now is I can use the second part to compute the definite integral, and all I have to do based on this equation right there, is all I have to do is take the antiderivative of, let me use a different color. All I have to do is take the antiderivative of the integrand, right? When I take the antiderivative of the integrand, that's going to give me these capital F's, right? And then all I have to do is plug in the bounds of my integral. I have to plug in the bounds of my integral into my antiderivative, and if I take the difference, boom, it accounts. It counts for signed area as well, right? So that's all I have to do to find my definite integral, right? And that's huge. There's no more giant rectangles, no more complicated summations. All it is this very handy little formula, right? So that's all I really want to talk to you guys about for today. If you guys have any questions, come see me during my office hours. And if you want to practice, I have a worksheet for you guys, and come to office hours and we can like really drill this into your head. I want doing the FTC part 2 to be as natural to you guys as kind of just adding numbers, right? I want us to be like really strong with this. So that's all I have for you guys today. I hope you learned something from this video. Thanks for watching.